Assalamu alaikum wa rahmatullahi wa barakatuhu. My dear student, welcome to all of you in this inorganic MSc and PhD combined class. I'm sure that all of you are listening to me clearly and you have no problem. If you have any problem, please try to inform me on time. Okay, dear student, today we are going to discuss one of the most important topic of our this course, and that is graphene based nanomaterial for catalysis. Basically, our this course comprise of different sections. First, we are preparing some material, then we are characterizing that material, and then finally we are using that material for some of our catalytic purposes. It may be electrocatalytic, it may be photocatalytic, or it may be some other thermocatalytic reactions, but our basic purpose is catalysis. So that's the main theme of our whole course. That is why I have selected this paper, which is one of the most important paper. That is, graphene is one of the most promising material these days used in electronic circuits or many electronic devices, and one of the very novel and highly versatile matter which are used. They are going to change even the nature of our electronics and some other material as well. And keep in mind, this paper was published in INEC, Industrial and Engineering Chemistry Research, in 2017. And the DOI I had given at the bottom, you can just look at the DOI, and I'm sure that you know about this information. That whenever you know about this information, you can easily track that paper very easily. And Science Hub, you know about that. Okay, now regarding the author, I just want to add a few words regarding the author, then I will proceed and discuss what we are going to deal in this paper. Keep in mind that there are authors, and this is the main author or the principal author, or you can call them the corresponding author, because the corresponding and principal, these are the two different things. This one is the corresponding author, and most probably he's a professor, Wang Xiangqin. Now, this is the principal author, that is Hu Mao Song, and Yao Hua is the other author. So it means this is a kind of a review paper. Keep in mind that is not a research article, that is a review paper. Okay, so that is the basic difference from the very beginning, that you know about this, that either this is a review paper or this is a research article. So keep in mind this is a review paper. Okay, and all of them, the affiliation of all these different scientists is from Department of Chemical and Biological and Pharmaceutical Engineering, New Jersey Institute of Technology, New York. Okay, US, United States. Now that is a little bit different from our culture or the European culture and Chinese culture. Basically, we write the first name and then the surname. In Chinese, it's the reverse of that. This professor, the name of this professor is Wang Xianqin, but it is written as in English. In Chinese, it is written as Wang Xiangqin, but in English, it is written as Xiangqin Wang, because Wang is a family name or surname. So there's just a lighter note on that. Okay, so that is today we will discuss this paper. Now, what is inside that paper? So keep in mind, graphene is considered one of the most promising material in a wide range. I told you in electronic, uh, it has almost manipulated the whole electronic industry these days. Optical, and then I will discuss some of its optical properties as well, thermal properties, mechanical properties, and why graphene have large application in a variety of material or in a variety of different disciplines. Why? Because it have large surface area. Now, just reminding you that what we had discussed in our class is that whenever we have some material, for example, we have a material like this. Okay, this is a cubic material. Now if we take this material in catalysis and compare with that small cube, and then compare with other small cube, and then a more smaller than this one, so we know that as we are going downsizing, catalytic activity increases. Why this catalytic activity increases? So I told you that this catalytic activity increase because of the increase in the surface area. So the highest catalytic activity is because of the surface area. And then we had differentiated surface area and active surface area. Okay, so that is one of the property of that is graphene. That graphene have large surface area, and that's the reason due to which it is used in a variety of applications. Now it have two-dimensional structure. If you just remind that we had studied before in great details that all the materials that we are going to classify in different sections. Okay, if you just remember, just for to remind you, that is we have a zero-dimensional object, sorry, and we have one-dimensional material as well, and we have two-dimensional material as well, and we have 3D material as well. Okay, so we have different classification, and I told you that nanomaterial is that kind of material who lies in the range of, let's suppose we are just defining a range for nanomaterial. If I just write down over here, that is the range for the nanomaterial. So it started from 5 nanometer, that is 5 nanometer to 100 nanometer, almost 100 nanometer. Okay, so this is just our classification of nanomaterial, and then beyond that nanomaterial. Okay, so it started from 5 up to 100. Okay, so any material whose dimension lies in this range, we call them a nanomaterial. Now it's not important that all the ranges, that is x-axis, y-axis, and z-axis. It may be possible that x-axis lies in that range, but y-axis do not lie in that range. Okay, no problem. It may be possible x and y lies in the same range of nano range, but z-axis do not lies in that range. It's also okay. Now, okay, 0D material is that kind of material whose all dimensions, that is x dimension, whose y dimension, and z dimension, all lies below the nano range. We call them 0D material. And I told you that our best example for that 0D material, if you just remember my last time discussion, so we had discussed that in great detail, and I'm sure that you will remember the example of that these are the quantum darts, okay, which is one of the most promising material also these days used in different application. Now regarding 1D material, if only one axis, that is x-axis or y-axis, okay, I'm writing here or y or y or z, if only one dimension lies in the nano range, we call them 1D nanomaterial. Now, the example of that 1D nanomaterial, maybe you remember the example of that we have different 1D nanomaterial, and these are nanowires, if you remember that nanowires. And we also know that we have different nanotubes, okay? Or these are the example of 1D nanomaterial. Now, if the two axes, like x-axis and y-axis, they lie in the nano range, then we call them 2D nanomaterial. And if you remember the example, we had discussed that the 2D nanomaterial, the example are nanosheets. These are the example of 2D nanomaterial. And then we have a 3D nanomaterial as well. Now 3D nanomaterial is that kind of material whose all the x-axis, like x-axis, y-axis, and z-axis, all of them lies in the nano range. Okay, and we call them nanocrystals. For the sake of simplicity, I will write NCS, nanocrystals. And then I had discussed that nanocrystals are of different geometric shapes. That may be cubes, that may be octahedral structures, okay, and that may be decahedral structure, and then maybe icosahedral structures. It means there are different geometric shapes for all these different nanocrystals. Okay, so just to remind you that we have a two-dimensional structure, and that two-dimensional structure is that of a graphene. That is why most of its area is came in contact with our reaction sites or with our chemicals. So that is why it's very important. And facile decoration, we can decorate anything on that surface. Now, whenever the surface, they have high surface area, they are two-dimensional, and they can easily come in contact with our chemicals. Of course, it have high absorption capacity. For example, if you take two examples, one is like, suppose one is this cube. Okay, so these have four different shapes, four different, like this is one axis, this is other one, this is other one. These are four different sides. Okay, and if I want to open that, so that is the first one, that is the second one, the third one, and the fourth one. So now the surface area is much more greater. There is no surface which is covered or which is inside. So that is the reason that it have highest absorption capacity. Why it's have highest absorption capacity? Because all these surfaces are openly exposed to the chemical reaction. Okay, now if anybody asks that how it's look like and what are its activity, how it can react, and what are its application in different dimensions. So it's quite interesting. Recently, if you remember, we had studied a lot of our study was focused on the CO2 reduction. Now graphene also play a major role in CO2 reduction. Just remember that. If you don't remember the exact mechanism or what are the specific derivatives of graphene, so just remember that graphene have played a major role in CO2 reduction. That is a one way that it is used. Okay, and CO2 reduction is a very hot topic these days, studied by a lot of researchers and a lot of scientists. The second one is oxygen reduction reaction. For this example, I'm sure that you remember our fuel cell discussion. Okay, if you remember our fuel cell discussion, then it's quite easy for you to understand that. Okay, and in our fuel cell discussion, I have discussed that in the fuel cell we have cathodic reaction and we have anodic reaction. For anodic reaction we have one of the wonderful catalyst, and that is platinum. But for cathodic side we have ORR reaction, where the oxygen comes in contact with the electrode and they take electron from the electrode, converting to O negative, that is O minus 2. Okay, and then it combined with that of hydrogen, that is H positive, and they can give us a water molecule. Now for this reaction, that oxygen reduction reaction, that is quite sluggish. Okay, and we need a fine catalyst for that. Graphene play a major role over there also. So there are two different dimensions. Okay, it also work in the air pollution. How you can say it work in air pollution? Okay, for the sake of simplicity, I will give you a clue over here. Because it's this graphene remove carbon dioxide from the atmosphere, and carbon dioxide is one of the major pollutant, so it also work in the pollution. Okay, that's one regime, although it's not 100% explanation for that term. Okay, what are others? There are also other heavy metals which are present in the water. There are also some pollutants, that is NOx, SOx in the atmosphere. They can also absorb, because we had discussed that the absorption capacity of all these material, uh, okay, I'm sorry, the absorption capacity of all these material is quite high. So when the absorption capacity of all these material is quite high, so it also removes a lot of material from the water as well, from the air as well, and from the solid compound as well, because it has absorption capacity, they have highest binding energy. Okay, it is also used for water treatment. Now you can easily explain that on which basis we can say it's used in the water treatment. Okay, it's also used in Fischer-Tropsch reactions. Okay, we can explain all these terms one by one later on. Okay, so whenever something has a lot of applications like that, everyone is eager to see that how it's look like, and who had discovered that, and what's graphene. Everyone is just want to find out what's the definition, how we can recognize that. Now just remember that graphene is a single layer two-dimensional sheet. Okay, that is very clear, and that is made of carbon atoms. That's not something unique for us, and all of them are chemically bonded by sp2 hybridization. That is important, the configuration, and that is like a hexagonal pattern like benzene. It's exactly the same, that benzene is spread on two-dimensional space. There are thousands of benzene rings, so you call them, and whenever you call them a graphene. Now whenever there is a word graphene, it must be connected with Ender Constantine and the other professor, Konstantin Novoselov. Now, okay, Novoselov professor, he born in I think 1974. Okay, and Professor Constantine Jim, he I think his date of birth is 1958, as long I remember. Okay, if I'm not wrong. Okay, and both of them have some common features. This is Professor Constantine Jim, and that is also Constantine, but this professor is Novosilov, and both of these professors have something common. The first thing, both of them are Russian scientists. Okay. The second point, both of them are not living in the Russia. They are working in England, in some Manchester University, and maybe they have just shifted to some other university these days. But later, in the previous days, they were working over there. Now, this professor is quite young enough. Both of them have discovered the two-dimensional nanomaterial nanosheet, that is graphene, in 2004. Okay, that is 2004. The fourth point, which is sheer and that is common between these two scientists, is that both of them are graduated from same institute. That is Moscow Institute of Technology, and both of them they have a major of physics, condensed matter physics. Okay, so there are some combinations and some common things, common features. Now, this professor, the professor Jim, he got a lot of awards during his life. Okay, he's still a young man and still living, but he got that is IG Nobel Prize in 2000, then Mart Medal in 2007, then Euro Physics Prize in 2008, then Corber Prize in 2009, then John J. Cartier Award in 2010, and then Haggis Medal in 2010, then Nobel Prize in 2010. Okay, a Nobel Award was given to these two scientists in 2010, uh, just as acknowledgement for the new discovery, highly potential material graphene, which was discovered by these two scientists. Okay, and this scientist, this Professor Jim, has also, he was awarded a Prince Sultan bin Abdulaziz International Prize for Water. So he have a lot of achievements over there. Okay, now this Nobel Award, I think I have discussed that in that class, that how much it worth and what does it mean, and there are a lot of benefits. So these scientists were given the Nobel Awards was shared by both of them in 2010 in physics. Okay, now graphene has shown many attractive properties. Okay, as we had discussed previously. So one of the property, that is quantum Hall effect, and that was the research thesis of one of these professors. Okay, now maybe some of you people know about the quantum Hall effect, and some of that you don't know. Sometimes it is also called integer quantum Hall effect, and it is nothing but it is the quantum mechanical version of the Hall effect, and it is observed in two-dimensional electronic system when it is subjected to a low temperature and strong magnetic field, which Hall conductance undergo quantum Hall transition to take the quantized value. This is called a quantum Hall effect, or we can also call them integer quantum Hall effect. Now, it may be a little bit confusing for all of you that, okay, whenever we are subjecting a two-dimensional electronic system, that is two-dimensional electronic system is graphene, to a low temperature and a strong magnetic field, and it undergo transition, and transition is due to that Hall conductance. Now, what is Hall effect? Now, it is the production of voltage difference across an electrical conductor. Okay, that is the production of voltage difference across electrical conductor, and transfers an electrical current in the conductor to the applied magnetic field and perpendicular to that current. So these are called just Hall effect. If you got the idea, well and good. If you don't got the idea, then there are also some other a lot important parameter as well, some other properties that you should keep in mind. So that is something about that is Hall effect. Okay, let me just change this. uh, okay, that is okay, that is a quantum Hall effect over here. I don't know, there is some problem over there. Okay, now the second point over here, that they have a theoretical specific area, specific surface area, that is 2630 meters square per gram, and that is the highest one, and that have highest high intrinsic electronic mobility. They have high Young modulus, and the Young modulus is almost 1 terapascal. That's also very interesting. And if you just look at this video, it's very interesting. The first thing that you should keep in mind, that what is Young modulus. If you just remind your previous knowledge, so that is just a mechanical property. Okay, it's nothing but it is measure of stiffness of any solid. So what does it mean? That graphene, which is seems to be a very delicate and seems to be a very thin structure and seems to be a very fragile structure, it is almost 100 times stronger than that of steel. The term you are using for that in your own language, that is folad. So it is almost 100 times stronger than that. Okay. How you can say that? Okay, let me give you an example for that. If you just look at this point, so that is almost 200 megapascal for steel, but it is 1 terapascal for that graphene. So it's much more stronger than that. What about its young modulus? So I told you that it is just the measure of stiffness. Okay, just keep in mind, or it's any mechanical property of any solids, and it's the ratio between stress and strain. And what's the stress is nothing but it is force per unit area. And what about the strain? And strain is also, if you just change in the volume per unit volume or change in length per unit length, so that is called a strain. That is a proportional deformation. Strain is nothing but proportional deformation, and stress is force per unit area. And if you take the ratio between them, then they call us young modulus. So young modulus for that graphene is very high as compared to that of steel or other metals. So in our daily life, we know that metals are very stronger, or they are very stiff, or they're very strong. They have the elastic property. They can come back to its original position. Even a high force is implemented on that, is well and good, but as compared to that, graphene is much more stronger than that. So it means it's very simple now that if we are using graphene instead of that material, so graphene show much more better property. Okay, that is mechanical property. Now what about its thermal conductivity? Now here the value is given that the thermal conductivity is almost 3000 to 5000 watt per meter per Kelvin. Okay, maybe you can imagine that it is high or low. So I will give you a clue regarding that, and then you can understand it quite well. That the thermal conductivity in most of our electrical appliances we are using these days copper, okay, or aluminum, or mixture of copper and aluminum. So if you just compare the thermal conductivity of the copper to that of graphene, so you will be shocked, because the copper have a thermal conductivity 384 watt per meter per Kelvin. Now 384, it's almost 400. You can just take it as a 400, and that is in above 3000 to 5000. So it's much more, 300 in the ratio of. So it means it's almost 1:10. So thermal conductivity of graphene is 10 times greater than that of copper. So that's a big difference, 1:10. Now, the transparency of that graphene, because you know it's a two-dimensional particle and it is made of carbon. Each carbon is connected to another carbon, and there is a pi electron that we will discuss later on. So, what about its transparency? So, transparency is almost 98%. It means it do not deflect or it do not deviate any kind of radiations they are coming. So transparency, we can also call them pellucidity sometimes, and sometimes we can also call them diaphanity. So all these properties of the transparency for that of graphene is also very high. Now here, if you look at just these few words, so it means the mechanical property of graphene is very high. Then the second one, we know that the young modulus, that is the mechanical property. That is the thermal conductivity of that is very high, and the third property, that is transparency, which is a physical property of allowing light to pass through the material without any appreciable scattering of the light. So these are the different properties on the basis of which the scientists they try their level best to give a new dimension to all the materials these days. Okay, now how it look like? It look like this structure, that each carbon is connected to another carbon in the same pattern as in the benzene ring. Okay, so in this way, benzene, the graphene look like in that way. Now, okay, slowly and gradually we move on, and we will study one by one that what are the properties of the benzene, the graphene, and how it is used for catalytic purposes, how it can be prepared. Okay, now coming towards its application side, as we had discussed before, that application side, there are a lot of application of graphene. Okay. there are a lot of application of graphene, but what are these applications? So it also used for separation purposes. So all those scholars who are working in separation technologies or separation of one chemical from another one, they can use graphene. How they can use? So it's a complete topic for discussions, and there are a lot of papers on graphene separation, because graphene, we know graphene since 2004. Now it's almost 16 year, but in that 16 year there are more than hundreds of paper only on that separation process. Okay, it can also use for environmental side. Now how it can use in environmental side, as I told you, that for controlling environmental pollutions, or for absorbing or pollutants in that. It can also use it at memory devices, transistors, transparent conducting electrodes. As I told you, transparency of that is more than 97 up to 98%. Optical modulators, surface enhanced Raman spectroscopy, sensor and dye sensitized solar cell, supercapacitor, batteries, fuel cell, catalysis, and even in medicine. So there are a lot of application. That is a broad spectra. So if any of the students, he or she is searching for one of the best topic, that how she can conduct his or her research very easily and conveniently, just prepare graphene and fabricate it with some of the other metals, and you will get a novel material that you can use for any of these different sections. Now irrespective of the differences, there some of them are working in organic side, and some of them are working in inorganic, or some of them are working in analytical side. So every discipline can use this for their own purposes, and their activity is quite high. Now we will discuss how. Now, due to its large surface area, good biocompatibility, and high absorption capacity for certain molecules, graphene and its derivative can be used as a valuable substrate to interact with the various species. Okay. Now, these points we had already discussed in details in the previous slides. That due to the surface area, what is meant by biocompatibility? Biocompatibility, that's a term that you use. Maybe you have already studied some other biodegradable, okay, and biocompatible. Now biocompatible means that if you use a material, and that material is not a living one, that is not made of cells or made of tissues, but that material, that is a material, that is a dead material like graphene, and you insert it inside a living tissue, and it is compatible with that, it means that the cell is not affected their normal routine life by that material. We call them a biocompatible. So it's a biocompatible. For example, these days you have heard that there are some kinds of wires and stretches that are being dissolved after healing of your wounds. So these are biodegradable compounds, and these are, graphene is a biocompatible, and it have a high absorption capacity for some of the molecules. So it means that there it can be used as a specific catalyst. It can be used as a catalyst by its own, or we can also fabricate its surface area by adding some of the catalyst. So these are some different uses of that graphene material. Now, whenever we know about this property of the graphene, that it have a very high activity, or it can be used for certain a lot of that is a, this range is a broader range. We can use anywhere that we want, even in the medicine, even in the catalysis, even in the synthesis, even in the atmospheric pollution control, or even in different sectors like in the physics, condensed matter physics, like capacitor, diodes, and these electronics. So everyone will think that how we can prepare that. So we can prepare that graphene by using different materials, different methods. These are different synthetic routes given over there. That is microchemical exfoliation. That is micromechanical exfoliation, chemical vapor deposition, exfoliation of graphite, oxide, and on surface chemical reaction. These are different methods by which we can prepare. They are synthetic routes for preparing graphene. Okay, I don't know, the sensor is not working, the reason behind that, still I don't know. Okay, so these are the different methods by which we can synthesize the graphene. Okay, but for the sake of simplicity, that I will tell you that when you prepare the graphene, then you can use it for different catalytic reactions. Okay, the first one that I will take is ORR reactions, and that is, I have already explained that how ORR work. Basically, that is oxygen, and oxygen is taking electron, and that electron is being taken from hydrogen, shifted to the oxygen, and that oxygen is converted to an O negative, and they give us a water molecules or hydrogen peroxide, or like that kind of a hydroxy compound. So that is, and that is one of the challenges, one of the major challenge in the fuel cell. So it can be easily controlled by graphene. The other one is, as I told you, that what is Fischer trap. So Fischer trap, here, for the sake of simplicity, keep in mind that it is nothing but it is the conversion of the gaseous fuel into liquid fuels. That's the most simplest one. You can consider this catalyst as any material or any catalyst that is fabricated by a graphene, or it is graphene by itself. It can use carbon monoxide and hydrogen. They can combine and they can give us liquid alkanes. So that is another application of that catalytic reaction. You can use for this reaction as well. Okay. There is another one, CO2 reduction. So CO2, as I told you, that CO2 we can convert it into some value added chemicals or some fuels. So some chemicals that you can use in the industry, and some fuels that you can use directly as a fuel. So this reaction that we had discussed is one of, in one of that our paper that we had studied for more than even a month, that how to electrochemical reduction of carbon dioxide. It totally just the total discussion is around this point. So you can also use graphene for this purposes. If you just remember, I told you that the lithium ion batteries, if you just remind and rewind your mind for some times, in lithium ion batteries we are using some different chemicals, if you just remember. And there were three different scientists in 2019, they were awarded a Nobel Prize on lithium ion batteries. Two of them, Professor Stanley and Professor Goodenough, they were from England, and the third one is Professor Yushano Akira, is a Japanese professor, and his total work is comprised of carbon nanotubes, carbon nanosheets, and all these different arrangements from the carbon. So that is also a one kind of catalytic reaction for which he has used carbon. And Professor Hure, who's one of the famous Japanese professor who had worked a lot of work on the CO2 reduction, that is metal-free catalysis. Because in every CO2 reduction paper, there is a one topic by the name of metal-free catalysis. So CO2, by using a sort of catalyst, and that catalyst do not contain any metal component, we call them metal-free catalysis. So you can use also graphene. And there are also some other application like water splitting. So from water splitting, what do we mean? So basically that is, even in our 10th grade or in our FSC, or even just in the initial stages of our study, we have studied that water can be split into hydrogen and oxygen. So graphene can also used. Even here, that is iron sulfide is given, that is a black cube given over here, but I don't mean that black uh, iron sulfide. Basically, this reaction can be happened by using a graphene, and some of the scientists have done a lot of work in that. And there are also selective hydrogenation. Sorry, there are also selective hydrogenation and NOx abatement, and then catalytic purification of volatile organic components and wastewater treatment. Okay. Now, what we get from this paper, if we study this paper thoroughly, so we can get a recent advances in its preparation. That people are preparing by using different methods, and what are these different methods, and how we can prepare this graphene. So we have different methods of preparation. Okay. Then the second point is our characterization. And for characterization, I have in the final 2-3 slides, and I wish that I can reach to these slides easily and I can discuss that. That's really very important for all the research students who want to do something in the research level. So how they can characterize their material. So for characterization, it's really very important. And that is one of the most important book, Catalysis and its Kinetics, Industrial Catalysis and its Kinetics. Later on, I will share the book with all of you. Okay. Now then, its application of graphene-based nanomaterial in catalysis, focusing on energy conversion, because energy crisis is one of the cry of the day, and then environmental protection and several other the same field, typical field. and what are the major challenges and opportunities for the future development. Because this paper that I have taken from 2017, so 2017 19 18 19 is not too old, but it's not too fresh as well. How you can design and fabricate graphene based novel nanomaterials, so you can also fabricate new material as well. Okay, now regarding nanomaterial, I told you that whenever you are preparing nanomaterials, you have two options. One is top down approach and one is bottom up approach. Now top down approach, I told you that in this way you are just, it's like a hammering process, that you are hammering a big particles, a clump, and then you are converting into fragments, and then you are hammering again. So in this way you are converting a bigger shape particle into a smaller one. Okay, now what about the this process, top down? Basically this top down approach is used by engineers, it's not by chemists. And the reason behind that is they are using some mechanical forces just to convert these big clumps of particles into a smaller one, and then they are using. But I told you that there are a lot of problems with that, and these problems, in this way you cannot get a pure uniform structure. Okay, the first one. The second one, that all the particles will not be a regular one, not a geometric one. Okay, and the third one, every particle, every time there is a probability of disintegration of the particles, because when once you hit, so you cannot control that. So in the same way, if you look at the picture, so the graphite, so graphite, there is a cleavage into graphenes, and there is oxidation to graphite oxides. It means that there is incorporation of any oxides, that is hydroxy group or carboxy group or some other groups, they are incorporated to that, and they are using in that way. Okay, so these are the methods that top down, that are not very efficient as well, because whenever we are using for catalytic purposes, then of course it's a problem, and that problem is that whenever, even if there is a single oxygen attached to that graphene sheet, then that single oxygen have the ability to attract or to gain an electron from the other catalyst, and to create a vacancy over there, which may be neglected in the bulk. But in electrocatalytic properties or in the electrochemistry, you cannot neglect that. So that's a bigger problem for us, that whenever we are using a top down approach. But by the way, different scientists have used that. And why they are using that? Whenever you are preparing anything, so people are just focusing on some parameters, that either the process is feasible or not. That is the first process, the first point. Okay, if you are preparing something by a feasible way, people will accept that. If you are preparing something by a non-feasible way, people will never accept it. The second one, either it is a reliable or not. If it is a reliable, is okay. If it is not reliable, then they will reject that. And the third one, it's versatile. The route is versatile or not. Okay, so if it is feasible, reliable, and versatile, so people have just discovered a lot of routes by that. And compared with that, the scientists realized that basically if we just compare any curved structure of that benzene rings, if you just combine a lot of benzene ring and prepare a curved structure, and you prepare fullerenes or soot or carbon nanotubes, then the single layer graphene, they are thermodynamically not stable in the free state. So when it is not free, so now you cannot control that. And there is a large scale of fabrication, you have a lot of problem with that. And they have a low reproducibility rate. So it's really very hard to deposit a catalytically achievable species on that inner surface. So there are a lot of problem with that. Okay, now there are one of the most developed methods to obtain a higher yield of graphene based nanomaterial is graphite oxide exfoliation. As I told you, that it is a micromechanical cleavage. So that is basically the exfoliation, and that is followed by a post treatment with a catalytically active species. So in the first step, what they are doing, in the first step, they are just exfoliating the graphite oxide. Then in the second step, then they are fabricating some electrically, catalytically and electrically active species on that. So these are the two steps of top-down approach by which they can prepare the graphene structures. Like here, there are two different images, not two, but basically there are three different images that I will explain one by one. So first of all, you should keep in mind that basically the whole process is divided into two steps. The first step, that graphite is oxidized, okay, into graphite oxide with various oxygen functional groups. First, they take the graphite, and that graphite is oxidized with the various oxygen functionalities. And that oxygen functionalities is hydroxy group, epoxy group, alkoxy group, or carboxy or carbonyl group. Whenever they just functionalize that graphite, so in the second stage, that graphite oxide is exfoliated by ultrasonication, or by mechanical treatment, or by any chemical treatment, or by any thermal treatment to produce graphene oxide. Okay, now basically what does it mean? Why we are going to functionalize that layer of that graphene or layer of that graphite by oxygen? So oxygen functionalities basically increase interlayer distances, because that is a big problem in graphene layer. Whenever you are combining all these graphene layer, preparing their graphene layers, so these are aggregated with one another. So whenever there is oxygen, so basically this oxygen increases interlayer distances of graphite oxides and graphene oxides, since the hybridization of the oxidized carbon atom is changed from sp2 to sp3. Because in the benzene ring, we know it is sp2 planar structure, but when it is oxidized with oxygen, it is converted to sp3. So that is the reason. Now this makes the graphite oxide layer. Okay, now that is a very important point. If you just look at here, because I told you that there are two steps. Now the two steps is very clear. The first one is graphite oxide is functionalized with oxygen, and we know that there are different oxygen functionalities, that is hydroxy, carboxy, carboxylic group, carbonyl group, or alkoxy, epoxy. There are so many other groups. Okay, that is the first one. The second, this graphite oxide is exfoliated by different ways. It means that the layer is being peeled off from one another by using different techniques: mechanical, ultrasonics, chemical, or thermal. These are different methods by which you can separate one sheet from another one, and you can prepare graphene oxide layer. Okay. Now, what is the advantages of that oxygen that we had already attached over there? So I told you that the basic purpose of that oxygen is just to increase the interlayer distances between the graphite oxide or graphene oxide layers. Okay. And I also mentioned that basically the hybridization of that carbon
Excuse me, sir.
atom, the oxidized
Excuse,
carbon atom, is changed from sp2 planar to sp3.
excuse
Now,
me, sir.
this makes graphite oxide layer hydrophilic, okay, whereas pristine graphite is hydrophobic in nature. And this
Excuse me, sir.
transforming the solubility makes its uniform dispersion of catalytic activities. Whenever you make this transformation in the solubility, then you are just providing an opportunity for any electroactive or any catalytical active species to fabricate or to uniformly disperse over there. Okay. By even they are very possible, and even they are very easy. And then this reduction, that is the last stage, that we can remove that oxygen from there, is by even by thermal process, or by a chemical process, or by any hydrothermal process, or by any soluthermal process, or by any photo reduction process. So these are the different purposes, different mechanism by which you can do that, and you can remove the oxygen from there. Okay, the basic difference between hydrothermal and soluthermal, that I will explain later on, that what is the basic difference over there. Now, the one other most important point, that intrinsic oxygen doped surface of graphene oxide hold a much higher binding energy towards the metal atom. Okay, whenever there is a metal atom, so that graphene oxide, which is already oxygen doped, it's having hold a much higher binding energy than pristine graphene, which would increase the stability and support catalytical active species and their resistance to centering, because there is a big problem of centering. So if the oxygen, the carbon is already doped with oxygen, then there is a big hindrance to that centering process, and their resistance, they also increase its activity. So these are the different purposes of that mechanism. Okay, now here, as we mentioned that there is the last one, that the redox reaction between graphene oxide and catalytically active species process allow the spontaneous deposition of catalyst nanoparticles. because I told you that whenever there is a redox reaction, so what is meant by redox reaction? Basically, that is an electronic business. That electron can be shifted from one of the species to another one. So from the one which we are taking the electron, basically is going to oxidize, and the one which is going to enter that electron is called reduction processes. So that is combinedly we can call them a redox reaction. So redox reaction between graphene oxide and catalytically active species. For example, we are adding or fabricating some material on a graphene surfaces. So that surface and graphene, which is now not graphene, which is graphene oxide, because we are going to remove that. Now, what happened that allow for spontaneous deposition of catalytic nanoparticles. So the dispersion of that catalytic active species is uniformly distributed over there. So that is one of the promising application of that. So these are the first preparation of that particles, which were given by, I told you that there are different scientists who invented for the first time. So along x-axis, y-axis, or z-axis, you can just look at its surfaces. So the figure A, which is given, that is the atomic force microscopy. Now the figure E is given the route, that how they can produce that, and there is a supporting material for graphene oxide, that is silicon oxide, and the last one, that is the D, that is scanning electron microscope of that, which is given over there. Now, okay, though the graphite oxide exfoliation method is shown excellent adaptability for catalyst preparation, okay, but still it's not free of challenge. Okay, there are a lot of challenges for this application. Now, what are these challenges? The first challenge, we call that the first we are going to convert that graphite to graphite oxide. Okay. Now, in the later stage, we are going to remove that oxygen, but that is not a complete reduction. That is so-called complete reduction. So that is a big problem over here. That is the complete reduction is a great deal over here, and that can also create a lot of problem for us. So that is a one challenge over here. Okay. Now you will be think about that okay, no problem, if we have oxygen over there, so can it create some problem for us or any hurdle for us? Of course it can. This residual defect is a great effect on its catalytic performance. Okay, if you are using any other field is okay, no problem, but if you are using electrocatalysis or you are using photocatalysis, so due to the severe influence on the properties including electrical conductivity, charge carrier mobility, surface roughness, electron band gap, and charge carrier separation. Okay, so these are so many other problems they are creating due to their residual defects. So the crucial role of graphene in electrocatalysis is to provide a network of high electron conductance to minimize ohmic losses associated with electron transport. Okay, so but unfortunately, due to the presence of that residual defect, it will significantly reduces the electron mobility, resulting into a limited electron transfer. As I told you that okay, you can neglect that one oxygen or two oxygen per unit area. In other, like if you are converting a biofuels or you, to some other by using some other mechanical processes, is okay, you can ignore that one or two oxygen, but particularly in photocatalysis and electrocatalysis, we are even taken into account of one oxygen, because one oxygen may consume two electrons, and their two electrons may create a problem because their two electrons is they are limited to electron transfer of that electrically catalytically active species, which is finally lowers the electrocatalytic performance. So that is a problem if we cannot take a pure layer of graphene incorporated by a metal atoms or by any catalytically active species, then we cannot get electrocatalytic high performance. Okay, then what we will do now? Okay, what happened in a typical photocatalytic system with graphene-based catalyst? Graphene is expected to play a role as an electron acceptor, okay, to enhance separation between the photo-generated electron and hole. Okay. Now, if you just remind the photoelectric effect when light falls on any material, electronics ejecting. Now, the graphene, they have the ability to accept that electron, okay, is just after illumination, which is accordingly to suppresses the recombination of the electron and the holes, and consequently they enhances the photocatalytic efficiency. Okay. Now the disadvantage mentioned above is due to the presence of residual defect. If there are some residual defect, it will lead to the sluggish separation of the undesired reaction performance. And this actual that is partially reduced graphene is generally far inferior, that are far inferior to the chemical vapor deposition method. Because I told you that we know about two methods. The first one is the top-down approaches. Until now, we are discussing top-down approaches. One is a bottom-up approach. And a bottom-up approach is a chemical vapor deposition. Now, chemical vapor deposition method is somewhat different from that, in which you are using a finely very pure structures over there. But in that case, in the that we had discussed, the top-down approach. The top-down approach will always create a problem for us, and that problem is due to, as I told you, that is not a complete reduction. That is a partial reduction, and that partial reduction is named as a residual defects. So that residual defects will create a lot of problem for us in the later stages. Okay. Now, what are the next? There is a very good paper that is high quality graphene by microwave reduction. And that paper is published by Waury et al. And that is a very interesting paper in the science. I think is published in 2016 or 15. I'm not sure about, but that is the paper that I will later on, I will share the link with all of you. And basically, if you just read it, this only abstract, so he had just mentioned that efficient exfoliation of graphite in a solution to obtain high quality graphene flakes is desirable. Okay, that is desirable in printable electronics, catalysis, energy storage, composites. He just counted a lot of applications. But how to do that? Basically, he used by a microwave reduction. Now, how he used microwave reduction? Here, I had given, okay, this paper was published in 2016. At the bottom, I had given the link. So from this link, you can easily understand that what does basically it means. Okay. I don't know this. The pointer of is not working. This terrible thing for me now, because I need to write a lot of things in this presentation, but unfortunately this is not supporting me at the moment. Okay, so why we basically he published this paper in the Science, and that is a very high quality paper, a lot of citation also. The paper is not more than 2-3 pages. I just suggested to all of you even to read a one paper a day, because these days you are free. So, okay, he used a very simple and rapid method to reduce graphene oxide into pristine graphene by 1 to 2 second long pulses of microwaves. Okay. What we had discussed previously, we had discussed we can prepare graphene oxide. Okay. And then we are going to reduce that graphene oxide. So there is a partial reduction and not complete reduction. What he had done, basically he used a microwave pulses, not for a long time, just for 1 or 2 seconds. And that microwave reduced graphene oxide exhibited pristine. It means it's also exactly same as that of chemically vapor deposition graphene-like features. Now you will just ask the question that how is possible that someone is going to prepare a microwave-assisted reduced graphene oxide is exactly the same as that of pristine graphene. Okay. Now his all data was supported by Raman spectra, by XPS, HRTEM, that these are highly ordered, in which the oxygen functionality are almost entirely removed. Now here it's really very technical, almost entirely removed, not entirely removed, almost entirely. Furthermore, that is the microwave assisted reduced graphene oxide showed exceptionally high activity for OER reaction. And some of the students, they know about this because they know they have read some review articles or some papers regarding that. Okay. So that is one of the just another approach is towards that mechanism, that there was a failure, and the failure was the exfoliation of graphite oxide layer. It was solved by the problem. That was a problem, and the problem was solved by one of the science paper in 2016 by Waury et al. And he had mentioned that if we used microwave assisted reduction of graphene oxide, then we can easily get a highly ordered structure of graphene. Okay, so that was a solution to that problem. Okay, now if you are using the CVD method, including other defect in mechanical exfoliation, you will get some foreign atoms sitting in a place of carbon. Okay, whenever we say pristine graphene, we means graphene in its original condition. Now, why I added this slide? Basically, I added this slide in the entire presentation. We are using graphene oxide, reduced graphene oxide, graphite oxide, reduced graphite oxide, pristine graphene. So some of the students will get confused that okay, what is the basic difference between pristine graphene and what is the basic difference between graphite oxide or graphene. So basically that is just for their definition. Whenever we are using pristine graphene, it means graphene in original condition or ideal condition, in which it's exactly hexagonal structure like benzene ring, and they are extending to infinity in every direction, that is xy direction. So they, and they don't does not have even a single defect in that. So that's meant by pristine. Okay, and that is only possible even by CVD method, not by any other methods. Now there are a lot of problems and challenges. Now here there is a cartoons of that, and it's just assumed to be that he is going to cook graphene, but he have a lot of problems in that. So this paper was published in 2013, received in 2012, but published in 2013, and that is also by Liu Jiayan, and that is also by Professor Huang Jiaxing. If you just look at the groups, most of the groups are similar. All those people who are working on graphene, most of them are interconnected with one another in some sorts. Okay, now how we can prepare graphene and what are the challenges and what are the solutions? So here he had just suggested some solutions. I will just discuss one of them. Now, the other issues related to the reduction procedure, because we told that there is a problem in the reduction process, not in any other process. So in the reduction process, there are also some related issues. Now, chemical, electrochemical, and thermal reduction of graphene into graphene oxide into graphene would lead to irreversible restaking or aggregation of graphene sheets. Okay, that's a big problem. Okay. Now, whenever you are using a method, now that method, no matter you are using a chemical method, electrochemical method, or any thermal method, by which you are converting graphene oxide into graphene, what will happen? There is a pi-pi interaction, and that pi-pi interaction will lead to the aggregation. Now that is a problem. How to solve this problem now? It may be retarded. Now this problem may be solved by intercalating catalytically active species. If we just add any catalytically active species who are there, okay, by the whole of Almighty Allah, we have just this pen start working. That's great. Okay. Now, so if we just add any electric catalytically active species who are there within the graphene layers, while in pseudosynthesis of reduction of graphene oxide, and the deposition of the catalytically active species occurred simultaneously for fabrication. Now, maybe you are getting confused with that discussion. Basically, it means that simultaneously you are adding something to that graphene layers, and you are also removing oxygen from that graphene oxide layers. Now, with this method, the formation of stack uh, graphitic structure would decreases. If, for example, if you have different stakes, like there are that is a one uh, piece, and that is another one, and that is the third one, and that is a fourth one. There are different sheets, and they are connected with one another. Now, at the same time, you are removing oxygen from that sheets, and you are adding some catalytically active species on that. Then there is a less chances for that it can be just attached with one another and aggregate with one another. Now, incorporation of catalytically active species onto that graphene or reduced graphene oxide surface with a good distribution may achieve a unique property. So that is a solution of that previous problem that we had discussed in the previous slides. Okay. Now, how you can do that? Now, let's make this story a little bit simple. Let's suppose there is a sheet. We know that graphene is like sheet-like structure. There's one sheet and there is another sheet. And let's suppose there is another sheets, a lot of sheets. So now what you are doing, there are two processes. And there are two processes, basically. The first process that you are converting graphene oxide into graphene. Okay. The second, you are decorating or you are adding some catalytically, that is catalytically active species. So whenever you are adding catalytically active species, basically it gives us a general idea that you are doing nothing, but basically you are, if there is oxygen like this, so you are replacing that oxygen by catalytically active species. So there is nothing new happened over there, and that is the hindrance for aggregation or accumulation of that sheets. So that is one of the solution of that problem as well. Okay. Now there is another way that just I told you just now, that simultaneous reduction of graphene oxide, and also we are also going to reduce some metal salts or something like that. So there is a paper which is also published in the same journal, that Industrial Engineering Chemistry Research, and that paper is published by Baumann, and that is really a very interesting paper. What he had done, basically he had to reduce silver. Okay, and I told you then all catalysis experiment, what we are doing, basically this all salts or all metal must be in the positive form, so they need electron. Okay, so when we add electron to that species, what will happen? They will give us a metal in the metallic form. So it means that silver is in the form of reduced form. Okay, so his first goal is to reduce that silver. The second goal, he also want to reduce, that is GO, graphene oxide, into graphene. So he have two problems at the same time, and he have to solve these two problems, that is simultaneously. And this paper was published in 2015. I can share later on this paper to all of you. Now, basically, what he had done both the methods at the same time. Okay, so now if you look at the morphology, that is the first structure, that is a nanoporous nitrogen and sulfur co-doped graphene, and then the pore size is up to 90 nanometer to 300 nanometers. So we can easily, just from the apparent structure, one can easily understand that, okay, nitrogen you can see here, sulfur over here, nitrogen over here, that is nitrogen over here. It means that nitrogen and sulfur are uniformly doped. Okay, this in this way he was succeeded. Okay, you can just look at this figure, you can easily understand that. Now the second process, that we can also see that the silver, if you look at this figure, the silver is also uniformly distributed over there. So graphene aggregation was effectively just prevented by using this mechanism. And later on, the expected reaction mechanism, if he is going to convert for water splitting. So for water splitting, that is maybe you can just look at here, there is water molecule and converting into hydrogen. So it's worked very well. So that is the one way by which we can use a simultaneous reduction of our graphene oxide and our salt. So the salt may be decorated on the surface of that graphene very interestingly, and we can get a uniformly distributed catalytically active species, and we can also reduce our graphene. So that is one of our interesting results that men had shown with us. Okay. Now there is another paper, and that paper was published by Hui. And that Hui, he proposed one part method. Now it may be a little confusing to all of you that what is meant by one part, which is my best way, by one of that I like the most, the process in I had prepared some catalytically active species by one part synthesis. Okay. Now, before just discussing this, there are some terms. The first one in this slide, there is a one part synthesis. Okay. The second point, there is a hydrothermal condition. What is meant by hydrothermal condition? Okay. I told you that later on in the slides, I just make promise with all of you that I will explain what is hydrothermal and what is soluthermal processes. So here I will just try to explain this one by one. Then later on, then I will discuss this slide. Okay. The first thing that what we need that is Teflon line autoclave. That is Teflon line autoclave. It's look like this. If this picture is clear to all of you, so that is a steel covering over here, and then we can cover that is its cover. We can just close it, and that's the steel rod. And this thing, if you can see it clearly, if you cannot see it clearly, now I can give you this picture, then you see it very clearly. Okay, remove this ink. Okay, now basically what I expect, it is also 20 ml, not more than 20 ml. It may be there are some Teflon line autoclave 50 ml, 100 ml. What we do, basically we just wet all of our chemicals. For example, you want to get some metals and you want to prepare some metal catalyst. Let's suppose that is a metal. So in the salt form, it will be in this form. So you must need to add something like that. So that is our metal salt, and that is our reducing agent, and then we can get this one. But that's not a very simple one. We need some capping agent. Also, we need some solvents. So in this method, usually we are using water as a solvent. Okay. Now, reducing agent, we can use any of the material. If you just browse your internet, you can find thousands of reducing agent used these days for catalytically active species. So we put our chemicals over there. Now, what will be our next step? We just put the reducing agent, our chemicals, and then we stir it for some times. Let's suppose there is a magnetic stirrer, uh, and then we put over there, like that is our this part, and then we stir for some time for uniform mixing. And after that mixing, we put in the oven. That is in which kind of oven? In this kind, all those students who has visited the UW lab complex, they see this kind of oven that we can put over there for fixed time. Let's suppose for 10 hours, 20 hours, or 30 hours. Then what is our next step? When the reaction is completed, then we take it out and we wash it. How we are going to wash it? Basically, we are washing and using centrifuge, because these are nanoparticles or nanomaterial. They are small enough. You cannot take it. It cannot be settled down at the bottom of that material. It will uniformly disperse. So by using that centrifuge machine, you can centrifuge. And there are some centrifuge tubes, and that tubes may be of different types. Some may be like this kinds, and all your material will be just over here. And then you can just add more water and just use a sonicator. How this it's look like? Sonicator is like that in order to uniformly disperse the material in your water. Okay, and then after washing, we are adding almost 1:5 with carbon, because our prepared material is quite less. They are not too much. So when we get 1:5, for example, if we have 20 gram of our material, then we add 80 gram of our carbon. It is activated carbon. So we loaded our material on the carbon, and then we are using for different chemical reaction. For example, if we are using for our electrochemical cell, so that is a potential state. So in this way, we are using it for to find out its electrocatalytic properties or electrochemical characterization we do by this. So these are the different stages in our experimental setup that we usually do whenever we are performing some experiment. But the point that I want to make over here is one part synthesis. I think that all of you know about this now, that what is meant by one part synthesis. One part synthesis is that you take the material, you take the reducing agent, you take the chemicals, the solvent, mix them together, put in Teflon autoclave, put it in the oven for 10 hours, 15 hours, and then at the end of the day, you take it out and your material is already well prepared. Okay, so now what he had done, basically he just proposed one part methods, and that method was for manganese oxide slash graphene synthesis. Okay, so what does it mean? Through a redox reaction between carbon of the graphene oxide and potassium permanganate through a reduction of graphene sheet. I think that now you have a very better idea about that. And in this way, he had achieved a finely dispersed, a well-dispersed manganese MnO2 manganese dioxide sheet. So that is one of the way that he had suggested. Okay. Now, whenever you take all your materials, the second point is your material characterization. Now, how to characterize your that material? For this, if you take the original parameters, like you take in the original condition all the things, and then you are suggesting something for that, because you know that there are a lot of things that are included in the catalytic activity of the material. So basically, catalyst may be a metal, oxides, sulfides, and some supporting material. And the whole structure may be very difficult for us to explain each and every phenomena at the same time. So for this purposes, we are taking the most simplest case, and then we are extending into a complex one. We are considering the most simplest and easiest case. Let's suppose we are taking, we have added some chemical promoters, and we are adding some structure promoters. And why we are adding some chemical promoters and structure promoter? Chemical that to increase its activity, and structure promote and even for selectivity, and structure promoter for mechanical promoters. So these are that we have just added. But let's suppose that we had removed all these promoters, and the substrate, which may not be a planar one, we consider as a planar one, because I told you that we are using a carbon, active carbon, as a supporting material to load it all active material on that, catalytically active material on the carbon, but carbon is not a planar one. But let's suppose we are considered, then we are going to characterize, and then we have to give them a model for that. Okay. Then how to investigate? Now there are different methods. There are spectroscopic methods for investigation of our catalyst. There are microscopic, and there are diffractional techniques by which we can just find out. Now here, this image, for example, this is your catalyst. Now, okay, if your catalyst is bombarded by electron, what will happen? Just imagine. Okay, if your catalyst is bombarded by, that is ions, if your catalyst is bombarded by heat, by photons, by electromagnetic fields, and by neutron, what will happen to your catalyst? Now basically your catalyst will get excited, and then when it comes to de-excitation state, then there must be a lot of information can be collected. For example, I'm just taking a one example. If you just give a heat to your compound, what will happen? If you just remember TG and DT study, okay, gives nothing but as a result of just heat. It is TGA and DTA studies. Okay, now I'm taking the another one. Let's suppose I just remove this, then I will take another one. If you are just using electron, what we will get as a result information? That is SEM, scanning electron microscopy, or transmission electron microscopy. If you are just, so all these different spectroscopic studies is nothing that, but first you are going to excite your material and then you are getting it back. Now, okay, how to characterize that? What researchers are doing, and what is the trend of the researcher these days? What they are doing in the different researches. So basically, this picture is taken from one of the conference, total paper published and total presentations. So how many peoples they have done their research? In how many people they have used different kind of material different techniques for their catalyst investigations. Some people they have used XRD. XRD is nothing, just you know about the XRD, that you are bombardment your material by X-rays, and what will happen as a result? Okay, you know about that. They will give us, do you remember the despacing and then the crystal geometry? So all of them will be concluded, and as a result you will get a peaks like this. If you just remember, in one of our class I have just discussed that if you don't remember anything, you can just remember only one thing, and that is about XRD, and that is nothing but if you just look at the graph, and that graph have peaks, sharp peaks like that. So your answer must be it is a crystalline and pure in nature. And if the peaks are like this, XRD peaks, then you say, okay, these are not crystalline one. So XRD, then BET. Most of the people, Browner, Emmett, and Taylor, why they are using this? This is for surface area, okay? So BET surface area, basically, it is used. And what is that XPS study that stand for? Basically, this irradiation of catalyst with your X-ray photon that can generate a photoelectrons, which are employed in X-ray photon spectroscopy, or XPS. Okay, and XPS it is the surface sensitive quantitative spectroscopic techniques that measure the elemental composition of that part. Basically, what XPS do, they do nothing but like that. Now, what about this UPS? And there are also some other methods. What is meant by this UPS? Because there is also a term UPS. That is ultraviolet photoelectron spectroscopy. As compared to XPS, UPS is limited to energy level, the valence electron. It means that this energy is limited only to the valence electron, but it measures more accurately the composition. Okay. So the other technique, that is TP technique. What do you think? Do you have any idea that what is meant by TP? Basically, when you heat one of your catalyst and heat a spent catalyst, and look what temperature reaction, intermediates and products desorption from the surface is temperature programmed desorption. That is a TP studies. Now then we have different kinds of that TP that I will discuss in one of the class. There is also some other non-familiar words to all of you. That is EXAFS, which usually most of the researchers they name that exhaust. That is extended X-ray absorption fine structure. And also there is XANES. That is X-ray absorption near edge structure. Okay. And what is this? There are also ESR. What is meant by ESR? So that is electron paramagnetic resonance spectroscopy. Okay. And the other, I think most of these terms are familiar, you also know about all these. But there is also one term that is LEED, that is low energy electron diffraction. Basically, that is a form of SPA LEED, that is spark profile analysis, low energy electron diffraction. And STM, you know about scanning tunneling microscopy. And there is also some other words, that is LEIS, like this one. What is meant by that is low energy ion scattering spectroscopy. Basically, MSI, that is mass spectrometry imaging, it can be divided into different fragments, and they give us a different information, that is that may be multi IMS, or they can be DSI, or they can be, there are other forms like SIMS. Now SIMS means secondary ion mass spectrometry imaging, and DESI means desorption electrospray ionization, and multi IMS means matrix assisted laser desorption ionization. So there are different terminologies they are used. uh, Later on I will just share the book with all of you, and then you can go through the chapter number 4, not very in the detailed studies, but you can just have a look to that book, and you will get a lot of information from that book. The only one thing,